Yeah, that's fine. That is correct. I don't, and I mean, it's more annoying if there's like a quiz or something, but Thursday, Friday, no quiz, so should all be good. And I just bought new batteries for the mic, so odds of the sound going wonky like they did last week are lower. So hopefully it'll work out okay. So I'm going to begin here by, it's a little bit old school. I'm reading King James Version today, but this is John chapter 1. It goes as follows. In the beginning was the Word, and the Word was with God, and the Word was God. The same was in the beginning with God. All things were made by him, and without him was not anything made that was made. In him was the life, and the life was the light of men. And the light shineth in the darkness, and the darkness comprehended it not. So that's John chapter 1. And of course it's talking about Jesus. And I think the original language that it was written in was, the word there, the word was logos, which was something that the Greeks of that time had sort of this belief that there was an order behind everything in the universe, sort of an impersonal, immaterial, sort of ethereal force that's behind everything. You see this belief sort of reflected in folks like Oprah, who talk about, you know, trying to get things from the universe as if there's some sort of, you know, energy that's everywhere, this sort of New Age mysticism. But that chapter in John is without equivocation saying that Jesus is the author and sustainer of the universe that we live in. And I just think it's encouraging. So anyway, I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. And again, I thank you for this class, for these students. Just ask you to just bless our work today. Help us to understand a little bit more about limits and how to calculate them and understand them. Lord, in your name I pray, Lord Jesus. Amen. So a little bit of technical jibber jabber here at the start. Definition, limit point. A limit point of U, which is say some subset of R, is a limit point, let's say P, is a point for which there exist infinitely many other points in U sufficiently close to P. Well, that's a mouthful. Now the definition that I have in the notes is written a slightly different way in terms of the open ball notation and so forth. But I guess I should make clear here, P does not have to be in U itself. Just to be clear, P itself, I'm not saying P is an element of U, I'm saying that if you're close to P, there's points in U. So let's just make it a little bit less abstract here. Let me illustrate. So let me draw a particular set in the color red. All right? So let's suppose we're talking about this set. It does not include the point -2. And then you got all these points here. It does not include the number, let's say 1. Go over here. Let's let it include the number 3. Then there's another point over here, let's say at 5. All right, and then, I don't know, that should be enough. So if I'm saying that the red points define a subset U, a subset of R, okay? So let's see here. Well, I guess it's probably a good exercise for me just to write it out in interval notation, right? That's probably something that would help you guys. Let me do that. What is U in interval notation? Let's see, so I'm going -2 not included, all the way over to 1. 1 is excluded, and then I go from 1 all the way to 3. 3 is included, and then I'm taking the union of that with the point over here on its lonesome 5. So limit points of u include what? So in short, the limit points of u include like everything from x equals minus 2 to x equals to 3, aka minus 2 included all the way to 3 included. So in particular, I'm most interested in the kind of sneaky case, which is that in particular minus 2 and 1 are limit points of u. All right. There's only one point here which is not a limit point, all right, which is that, 5. So 5 is not a limit point. And the reason for that is that if you think about an open set around 5, see this? If you think about an open set about 5, it's not the case that for arbitrarily small open sets around 5, they necessarily have infinitely many points in the set U. That's what we would mean for it to be a limit point, is if you shrink down and you take a little open set around that point, it has to have many, 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 infinitely many points inside U for it to be a limit point. All right? And 5 does not have that. 5 is what's called an isolated point. So you might ask, what's the point of all this? I regret nothing. It's that we can take a limit of a function, all right, if at a point, if that point P is a limit point of its domain. So this is essentially the story. We have limit as x goes to P of f of x. All right, makes sense. At least as a, something we can attempt to make sense of, provided that P is an element, P is a, let me just say, is a limit point of the domain of F. Let me put this into practice for some concrete sort of simple examples. So example 1, if we were to try to take the limit as x approaches, say, minus 1 of the square root of x, what would you do? What should you tell me if I say, hey, go calculate the limit as x approaches minus 1? Probably should tell me something like, Professor Cook, did you proofread this test before you gave it to me? And I'd be like, well, I was in a hurry. What's wrong? And then I'd be like, oh, yeah, so that problem's not right. That limit is something we can't even entertain, right? Because minus 1 is not in the domain of that expression, right? It's not even close, is the point. It doesn't have to be in the domain, but this is outside the domain, right? Like the domain of the square root of x is what, 0 to infinity, right? Minus 1 is over here. That is not a limit point for this expression. Example 2, so this is, not even reasonable. You could write it doesn't exist, but it's in some sense, this is beyond doesn't exist. This is not even a well-defined limit. All right, we don't even have a really standard language to discuss this case, truth be told. All right, example 2. What if we had something like the limit as x goes to 2 of x minus 2 over x squared minus 4? How would we think about this limit? So is 2 a limit point in this case? So this, if I call this thing f of x, what's the domain of f of x? So yeah, like x such that what? X is not equal to plus or minus 2, right? So if I draw the domain on a number line, it's missing minus 2 and it's missing 2, right? But everything else is in there. So this expression, What are the limit points of this expression? Well, everything. You could take the limit of this anywhere. It may or may not exist, all right? It may or may not exist, but at least we could take the limit, all right? Then that begs the question, well, how do you take the limit of something like that? Do you guys want to tell me? And eventually I'm going to do my due diligence and write down the limit laws and prove a few of them for you, but just let me finish this diatribe here. So this is x minus 2. And I heard one of you guys saying something about factoring. That sounds like a really good idea. So we do that. And then what happens? Remember, this is the limit as x approaches 2, which means that x gets close to 2, but it's not equal to 2 in this process, which means we're well within our rights to cancel the offending this guy and that guy, right? And when we do that, we've got the limit as x approaches 2 of 1 over x plus 2. All right? At which point, we can use the limit laws, which I haven't even written down yet, and plug in 2, and we get what? 1 over 2 plus 2, which is 1/4, yeah. So the answer here is the limit exists and it's 1/4, but yeah, 2 is a limit point. All right. So let's see here. What happens? What if I take, on the other hand, let's pick on this example a little bit more. What if we take the limit as x goes to minus 2 of x minus 2 over x squared minus 4? What happens then? I mean, I can simplify it the same way, right? It's still true. The same algebra that we did above holds. So we have limit as x goes to minus 2 of 1 over x plus 2, right? How does that work out? So that's a question. What's that?
You can't divide the 1 by the 0.
Yeah, we've got 1 over 0. And there's no 0 upstairs either, right? It's just this limit has type 1 over 0, which is not indeterminate. That just blows up. So this one here was type 0 over 0, right? And then this here was, no longer 0 over 0. I don't have it. I mean, this is just, that's not an indeterminate type. That's a determinate type. In other words, I can just plug the number in and solve the limit. So if it's indeterminate, we usually have to do algebra to remove the indeterminacy, which we did. However, this one here, we did the algebra we can, and it doesn't fix anything. Like this is type, if you like, basically minus 4 over 0, It's type minus 4 over 0. That doesn't, there's no hope for that. It's going to diverge. How does it diverge? Well, there maybe a graphical approach is wise, yeah? What's the graph of y equals 1 over x plus 2 look like? We know how to graph rational functions, right? So it shouldn't be a lot of mental effort for you to write this graph down, right? There you go. That's y equals 1 over x plus 2. So what's the answer here? As it stands, the answer is does not exist. Why is that? Because the limit as x goes to minus 2 from the right of, let me just give this thing a name, let me call it Pac-Man, is equal to infinity, whereas the limit as x goes to 2 from the left, minus 2 from the left of Pac-Man is equal to minus infinity. I'm calling this thing Pac-Man altogether. And that's clear from the graph and the reduction, yeah? What's the graph of Pac-Man look like, by the way? What is it? What's that?
A linear function.
It's a linear, no, I'm not,
We're talking about that.
let us be clear, Pac-Man is this. What is the graph of Pac-Man? Look, it's the red graph that I already drew here, right? With a what? What happens at 2? What's here? That is a hole in the graph. The hole in the graph is at 2, 1/4. That's why the limit exists, because it's just a hole in the graph. All right. Let me tell you the limit laws. Okay, so here we go. Let us collect our favorite limit laws so that we can do things in an orderly fashion. We'll find my list. So this is section 2.3. At the start, I have this list of limit laws. And so like number 1 is that, I'll just write it this way. The limit is unique if it exists. All right. So if you calculate the limit and it exists, good news, you're done. You don't have to worry about calculating it a different way and getting a different answer. Like that's kind of boring to even write down, but well, sorry. What can I tell you? It's a property. If the limit as x goes to a of f of x is equal to L sub f, and the limit as x goes to a of g of x is equal to L sub g, then the limit as x goes to a of f of x plus g of x is equal to L sub f plus L sub g. In other words, the limit of the sum is the sum of the limits, provided that the limits in question exist. 3, you can pull a constant out of a limit. Again, provided the limit exists, all right? 4, the limit as x goes to a of like c1 f1 plus c2 f2 plus da 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 plus cn fn of x is equal to c1 limit as x goes to a of f1 of x plus c2 limit as x goes to a of f2 of x plus da 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 plus cn limit as x goes to a of fn of x. Five, the limit of a product is the product of the limits. Again, these all assume that the subsequent limits exist and are real. If the limits don't exist, it's more complicated. Six, the limit of x goes to a of f of x equals to L1, and if the limit as x goes to a of g of x is equal to L sub g. Oh, my bad. Let me fix that. The limit as y goes to L1, my bad, of g of y is equal to LG. Then the limit as x goes to a of g of f of x is equal to L sub g. And then there's 7, which is that the limit as x goes to a of f of x over g of x is equal to the limit as x goes to a of f of x divided by the limit as x goes to a of g of x. There is a term and condition applied here, which is that both the limits have to exist. And of course, the limit of the denominator must be non-zero. Finally, last but not least, we can do a substitution for limits in this following sense. The limit as x goes to a of f of x is equal to the limit as h goes to 0 of f of a plus h. All right. I regret not just copying this page and handing it out to you today, so I didn't have to write these things, but you should write these things down and meditate upon them, because these you need to know. These are tools of the trade. These are what we use to solve limits, at least for now. Now, I don't expect you to be able to prove all of these, but there is one I usually prove in class, and I usually ask that you be ready to prove the same if I was to ask you. So, you know, so let me show you it's our proof for today. All right. I suppose there'll be two proofs for today, but this is one of them. Let me start out with the easy one. This one's kind of this one's actually not even on this list. The proof I want to show you, it's just exceedingly silly, but it is important. It's basic to what we're doing, and it does come up a fair amount. And that proof is this. So example 3. I want to prove to you guys that the limit as x goes to, oh man, it's still wet. Still wet. I want to prove to you guys that the limit as x goes to a of x is equal to, what do you guys think? So the rightmost board, this is all the start of section 2.3. If for some reason you can't read part of that on the board, it's all the start of section 2.3 in my notes. And there it's stated a little bit more carefully. In the notes I actually have emphasized what I'm assuming exists and so forth. So you guys tell me, what's this equal to? Yeah? A, very good. You're like, is this a trap? No, it's not. All right, so to prove that this limit exists, what do we need? We need to choose a delta greater than 0 such that the absolute value of x minus a is less than epsilon, right? And we control what? We get to control 0 less than the absolute value of x minus a less than delta. Like, we can, so the way the proof works is we have to, every proof from the limit definition starts like this. Let epsilon be greater than 0. If you write, let epsilon be greater than 0, and that is clearly the start of your proof, you have just earned 20% of the credit for the proof, right there. Everybody can do that, right? So I want you guys to get 100% of the credit for these, but that's the starting point. These all have to start like that. Yeah? What?
We have to write a proof for the proofs for the answers if we have that type of question in the quiz test.
Yes, but I would clearly ask, the language would follow, the following language would be used. Prove this limit is such and so forth from the definition of the limit. If I don't say prove from the definition of the limit, then you are free to use limit laws, pre-calculus graphing techniques, and everything else. But if I say from the definition of the limit, then that means from the definition of the limit, which is what I'm doing right now. So let epsilon be greater than 0. And now we must select, choose delta equal to what? What should I make delta equal to? So like generally speaking, this delta is our choice. The main part of the proof is selecting delta as a function of epsilon. Delta will be some kind of function of epsilon usually. This one's so obvious, it's so silly. It's you probably have thought of it, some of you, but are afraid to say it. Just say it. What is it? A. Oh, good. That's a good guess, but no. Nope, not one. Good guess, but no. Epsilon. We have a winner. Epsilon is greater than 0. We need delta, so it's greater than 0. Great. If 0 is less than epsilon value of x minus a is less than delta, then the epsilon value of x minus a is less than epsilon. Hence, the limit as x goes to a of x is equal to a. Done. This is kind of silly, isn't it? Yeah. I can show you guys one where delta equals to 1 works. You want to see that one? Check this out. The limit as x goes to a of a constant. What's it equal to? If I ask you, what's the limit as x goes to 7 of 3, what's the answer? Not 7. The constant, it has nothing to do with a. It's the constant. So the limit, the value of the limit depends on the function we're limiting, not the limit. Well, it does depend on the limit point too, but we're talking, the limit is the y values. So here, it's just a constant. So check it out. Let epsilon be greater than 0. Choose, you guys told me to choose delta equal to 1. That's greater than 0. Note, the 0 less than epsilon value of x minus a less than delta equal to 1 gives, actually it has nothing to do with it. It really has nothing to do with it. Then the epsilon value of c minus c, right? So this is my f of x. This is my L in the language we were using for the definition yesterday. What's the epsilon value of c minus c equal to? It's the epsilon value of 0, which is less than, right? Aw, man. Oh, which is less than epsilon, yeah. I'm sorry, I got stuck for a second there because I'm a moron. It has nothing to do with delta whatsoever, right? You could make delta equal to 42. It doesn't matter. It's like proving that the limit of a constant is just dumb. But there it is. Thus, the limit as x goes to a of a constant is equal to a constant. All right, let me do, I need to show you the proof of 2. All right, that's something we usually do in here. So let me show that to you. The proof of 2 does require a little bit more, what's the word? Sneakiness. All right, so let us assume, so limit law 2, which is, might call it additivity. Additivity of the limit. So let us assume that the limit as x goes to a of f of x is equal to L sub f, and that the limit as x goes to a of g of x is equal to L sub g. We want to show, and we're assuming both L sub f and L sub g are themselves real numbers, okay? My claim is that the limit as x goes to a of f of x plus g of x is equal to L sub f plus L sub g. So let me try to show you what's involved here. What do we need to show? We need to show that if we're close enough to the limit point, we can make the values of the sum of f and g arbitrarily close to L sub f plus L sub g. So like, here's our target, right? We want to look at this. We want to have f of x plus g of x minus L sub f plus L sub g, right? We're trying to show that this is less than epsilon, right? We'd like to make that less than epsilon. That's our goal. Okay? That's our goal. So here's the proof. Let epsilon be greater than 0. I got 20% credit already. Sweet, right? Since limit of f and g at x equals to a are given, we may select delta f and delta g greater than 0, for which 0 less than the absolute value of x minus a less than delta f implies that the absolute value of f of x minus L sub f is less than epsilon over 2. And I can do the same for g. See, because the limits of f and g are respectively given, all right? Which means I can make the values of f and the values of g as close to L sub f and L sub g as I like by taking inputs sufficiently close to the limit point a. All right. Let delta equal to the minimum of the delta f and delta g. All right. You guys know what a minimum is? Like if I give you 5 and 7, what's the minimum? 5. If I give you 0.05 and 0.0000003, what's the minimum? The second one, right? So if delta is the minimum of both delta f and delta g, we have that, among other things, you have delta f is less than or equal to delta and delta g is less than or equal to delta, right? Wait a minute. Is that right? Other way around, right? My bad. Right? Other way around. Other way around. It's the minimum, right? So it's smaller than both of them. Okay. Consider this then. If we have the absolute value of f of x plus g of x minus L sub f plus L sub g, right? That, I missed something. Assume 0 is less than absolute value of x minus a is less than delta. Okay? For such x, consider the following. The absolute value of f of x plus g of x minus L sub f plus L sub g is straight up equal to the difference of f of x and L sub f plus the difference of g sub x and L sub g. But there's something we know for the absolute value function, which is called the triangle inequality. The triangle inequality says that this is less than or equal to the absolute value of f of x minus L sub f plus the absolute value of g of x minus L sub g. This is the triangle inequality. Okay, but what do we know? We're assuming that delta is the minimum, right, of delta f and delta g. What's that mean? That means for such x as I'm considering, I get to have my cake and eat it too, right? I get both this and that. They're both in play. So this is straight up less than epsilon over 2 plus epsilon over 2, also known as epsilon. Therefore, we have shown for such x, the difference of the sum of the functions from the sum of their limits is less than epsilon, which proves my claim from the definition of the limit. All right? So, actually, I don't usually ask for this on test 1 in here, but it's, you know, if I was to expect you to prove this on test 1, like, I will tell you, so you'll have forewarning. But it's good for you to understand. What you're more likely to see on test 1 is a proof like the example I did last class, or a quadratic example, both of which will be in your homework, which I will be announcing the problems of sometime soon. I was going to do it last night. I fell asleep, so sorry. It was a long day. Uh-oh. Did I remove the camera? I did, okay. All right, so this is good news because it means that if we have a limit of a sum, we can break it up into pieces, right? If it's helpful. Now, as I was warning you guys, the proof of the some of the other limit laws is pretty touchy, especially like the product rule. I might make like a supplemental video about that in case anybody's interested. If I do make that video, you're not expected to watch it. It's not part of the required content of the course. All right? It's just, it is pretty technical, the proof of the product rule number 5, but it is true nonetheless. Okay, so example, where are we? Man, you guys have to help me out. Was that example 3, example 4? I can't remember. 4. Cool. So let's put these things together logically. How about if we have the limit as x goes to a of x squared? How could we do that if we're assuming that we know the product rule? That is what? That's the limit of x times x, right? That's x squared, yeah? So if we accept limit law 5 as being true, we've got this and that, right? Which is, we proved it just a second ago, that's a and that's a, so we get a squared. The limit as x goes to a of x squared is a squared. This is not too surprising, right? And likewise, if we do the limit as x goes to a of x cubed, how's that going to go? What's x cubed? Yeah, x times x, or x times x squared, right? So using the product rule for limits yet again, limit of x goes to a of x times the limit as x goes to a of x squared, we get what? A times a squared, which is, all right. So I think you guys see where this is going. What can we cipher from all this? In general, the limit as x goes to a of x to the n is a to the n, right? I'm assuming, of course, here n is a positive number. But that actually would still be true if n is a negative number, provided a is non-zero. All right. How about this? What if I have like the limit as x goes to a of, say, 3x squared minus 7x plus 2? How would you do this? So if I'm gonna do this in terms of limit laws, man, this umbilicus is gonna kill me one of these days. So let me write it out. So we've got limit as x goes to a of 3x squared fine, plus the limit as x goes to a, don't get used to this, I'm only doing this for you guys once, because like this is a drag. All right. But there are calculus instructors in this world who spend weeks and weeks in Calculus 1 doing this. I'm not that person. Okay, so what did I just do? I used limit law. I used the additive property, right? Twice, actually. Truth be told, I used what we just proved 2 times to do this. Then what? I can use the constant pulling out property to pull the 3 out. And the 7, minus 7 out, right? What's the limit of 2? It's 2, right? We worked it out for c. It's still true when c equals to 2. And how's this work out? So we've got ourselves a 3a squared minus 7a plus 2. There you go. All right. So I pretty much never ask for students to do it like this because it's just, I don't think it's interesting in here. What I will typically say is something like calculate the limit using limit laws and maybe common sense. All right. So the common sense extrapolation of this calculation is what? What can you guys tell me about a polynomial? If we have p, p of x is like an x to the n plus dot 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 plus like a2x squared plus a1x plus a0, and you calculate the limit as say x goes to, let's say, b of p of x, what's it going to be equal to? So this little theorem, if you will, is the logical extension of the last couple examples I just did here. The laziest way to write it would just be p of b, right? In other words, we just plug in the limit point into the polynomial. Specifically, what that means is like an b to the n plus dot 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 plus like a2b squared plus a1b plus a naught. So what I'm trying to tell you is that to calculate the limit of a polynomial at a point, what do you got to do? Plug it in. Simple as that, right? Any questions? Comments? Concerns? All right, let's try some harder ones, yeah? Oh man, time flies when you're having fun. So let me warn you guys that, and the same is going to be true how about rational functions? How do the limits of a rational function work? So here, you have f of x is equal to what? P of x over q of x, right? So if I was, say, taking the limit as x goes to, let's say, a of, p of x over q of x, how would that go? What's that equal to? I've got a p of a over q of a. I'm liking it. Now, why didn't I just use that earlier today? Because like earlier today we were calculating the limit of a rational function. Yeah? What was it, x plus 2 over x squared minus 4? I think, or something like that. That's a rational function. Why didn't I just use that there? Ah, yes. So you're not wrong, but there are strings attached, right? It's literally just this. If what? Q of a is not equal to 0. What's the rest of the story? What if Q of a is equal to 0? Well, if Q of a is equal to 0, and P of a is not equal to 0, then it blows up. To use a technical term. I'm joking. It depends then on the details, but it could be goes to infinity on one side and minus infinity on the other. we'd say it does not exist in that case. It could be that it goes to infinity. It's like a volcano goes up, or it could be an infinite pit that goes down. So the limit could be plus or minus infinity. So basically, in this case, depending on the details, it's either going to be plus or minus infinity or does not exist. All right? On the other hand, if Q of A is equal to 0 and P of A is equal to 0, well then the limit as x goes to A of P of x over Q of x is type 0 over 0. All right? It's type 0 over 0, which means we don't know without further investigation if the limit exists or doesn't exist and what its value is. All right? So what we're going to be looking at tomorrow is a bunch of examples where we're just focused on applying limit laws to calculate specific limits. So like tomorrow is the heart of the calculation you need to learn for this part of the course. All right? So like tomorrow we'll do a bunch of examples. I probably won't prove anything tomorrow, but anyway. Enjoy your, we got convocation today? Is anybody interesting? No? No? Okay.